So you have a right angle triangle. I always like to imagine the right angle is on the right, and then you have some angle on the left. And then you have your hypotenuse that goes across diagonally. And so the sine of the angle on the left side is going to be equal to opposite over hypotenuse. So it's just a ratio between the length of the side that is opposite to the angle divided by the length of the hypotenuse. That's literally it. Mm-hmm. And then cosine is adjacent over hypotenuse. Again, same thing. And then tan.
Not same thing. I mean, it's a different. Well, no, it's a different side.
Same thing, like different.
Yeah, I
like,
mean, it's dealing with the
idea.
adjacent side instead of the opposite. But yeah,
you just take the adjacent. Yeah. For tan, you have opposite over adjacent. Again, opposite length of opposite side over length of adjacent side. And you can also think of it as sine over cosine.
That is how it's defined. Tan is defined as sine over cosine, which simply equals opposite over adjacent.
Mm-hmm. Because the hypotenuse cancels out when you do the ratio. So that's what they are. Why is it useful, Rehan? Maybe you want to touch on
why are sine, cosine, tangent useful? So, well, the first thing about these things is that, well, they are ratios, right? It's not a value that has, a unit to it. It's not that it has any meaning. It is simply a ratio between these two sides. And the advantage of that is that these ratios can be applied to anything. So if, let's say, I have a triangle that has a 30-degree angle and has some length, some side, and I just expand it to a really large level, but keep the angle the same, the ratio of everything stays the same. And that's the beauty of trigonometry as well. That no matter how big things are, as long as the proportionality of all of them remains the same, so like the angle stays the same, we have the same proportions. So basically we have the same ratios. So sine goes from from -1 to 1. So it simply has this, back and forth oscillation, and where we might get into, sine graphs and stuff like that. But before we touch into...
Actually...
Do we want to touch into graphs right now?
No, I was just going to say the reason why it goes from -1 to 1. Yeah. And this is the visualization tool that everybody uses. So we have the unit circle. You draw a line from the origin to the side, or any point along that circle. And then what you do is you create a right angle triangle by, extending out from the origin along the x-axis, and then from the x-axis up to that point, you're going to get a right angle triangle. And now in this case, this is a unit circle. So the hypotenuse is 1. So sine of our angle actually just reduces to the opposite side, because it's opposite over hypotenuse, but it's opposite over 1. So the sine of the angle is just the length of the opposite side. Same thing for cosine. The cosine of the angle is just the length of the adjacent side. Now, you can... this is always so hard to do without actual visual aid. Yeah. But as you start from the x-axis and then you go counterclockwise around your circle, you can... I feel like this is so hopeless to describe with my words.
Let's try it. You can try it.
The cosine, right, the adjacent side is going to start at 1, go to 0, then -1, and then back to 0 and back to 1. And then the sine is going to start at 0, grow to 1, 0, -1, and then back to 0.
And again, all of that was simply the length of the opposite. Like if you simply think about it, right? Like when it's completely flat, the opposite doesn't exist, but the adjacent is 1, right? So like just think of that. Right. Yeah.
And the reason why this is like a cool thing, I guess, is because if you plot sine, like the sine of and the angle versus the angle, right? You're going to get this wave pattern. And the same thing with the cosine. You're going to get a wave pattern that oscillates between 1 and 0.
No, 1 and -1.
And, 1 and -1. And the reason why this is so useful is because now we can model things that oscillate. Like, for example, waves themselves,
Yep.
or springs,
Yep.
or maybe you're on a Ferris wheel and you can say, graph your height off of the ground. Well, if you're on a Ferris wheel, your height starts, at some point, and then it oscillates between the bottom of the Ferris wheel to the top of the Ferris wheel at a constant rate.
Something even simpler, you can just think about like a mass on a spring, right? Like if it's going up and down and up and down, it's basically oscillating. So there's some center.
Wait, sorry.
Yeah.
I misspoke. I said your height changes at a constant rate. I meant the wheel is spinning at a constant rate. The height doesn't change anyways.
Oh, okay, yeah. But anyway, so like as I was saying, you can just think about like a mass on a spring, for example, right? Like you have that equilibrium point, like at 0, and then it's kind of oscillating between going up and going down and going up and going down, and that motion can be represented as a sinusoid. Now, what is amazing about these sine graphs and the cosine graphs is if you plot them on the same axis, you'll see something where you can understand the relationship between both of these trigonometric functions. Man, my mic is falling. So the interesting thing about the sine and cosine is that cosine, if you look at the graph of it, it is almost identical in the pattern. It is identical to that of a sine graph, except it is shifted just a little bit. Now, why might that be? That's simply because of the inherent property of how we define sine and cosine. That at 0, what am I trying to say?
The origin?
Not at the origin, but like at the
as an angle of 0.
Yeah, like the angle of 0, exactly. We have opposite equals 0 and adjacent equals 1. So we have sine equals 0, cosine equals 1. So basically the idea between sine and cosine is that they are complementary. So a sine of 35 degrees, or for example, the common example is sine 45 equals cosine 45, right? And then from there, like you can think about any other variation. For example, we have, sine of 40 will equal cosine of 50. So they are basically these complementary angles. That means if you add them up to 90, they will be the same. And the simple reason is because that is inherently how they are defined. When we have sine equals 0, cosine equals 1, and we start moving across the circle, you will literally see them just switch. They will be kind of going in a pattern where they're going towards the center, so they're oscillating towards the center, and they're going back and forth. They're meeting in the center, and they're simply going back and forth. So when this is 1, this is 0. When this is 0, this is 1. And that's simply the idea behind their oscillation. So even though their pattern is identical, it is simply shifted a little bit. And that is where we can use sines for everything.